Hello everyone, my name is Minwoo Cho. Today I will present my project on data-driven equation discovery of Duffing oscillator using Cindy framework. Understanding governing equation is fundamental to describing and predicting physical systems. In classical mechanics, we typically derive this equation from first principle. However, in many real-world problems, such as complex materials or biological systems, the underlying physics may not be fully known, or the systems may be too complicated to model analytically. This motivates the use of data-driven approaches, where we attempt to discover the governing equations directly from observed data. Such approaches are particularly important in modern scientific machine learning, where we aim to combine data with physical structures. The objective of this project can be summarized as follows. First, we aim to recover the governing equation of nonlinear dynamical system from trajectory data using the Cindy framework. Second, we investigate how measurement noise affects the accuracy of equation discovery and whether applying denoising techniques can improve the results. The main method used in this work is sparse identification of nonlinear dynamics, or SINDY. The key idea behind Cindy is that many physical systems, even though they appear complex, are actually governed by only a small number of dominant terms. Instead of assuming a specific model form, Cindy tries to discover the governing equation directly from data. To do this, we first construct a library of candidate functions. This library includes polynomial terms such as x squared, and x cubic, as well as velocity terms, interaction terms, and external forcing inputs. For example, in our case, the library includes terms like displacement, velocity, cubic nonlinearity, and forcing. The idea is that the true governing equation can be represented as combination of only a few of these candidate functions. Once the library is constructed, we express the time derivative of the state variable as a linear combination of these functions. This gives us the regression form shown as x dot equals set of x multiplied by the psi, where set of x is the library matrix evaluated from data, and psi contains the coefficient we want to identify. Now, the key step in Cindy is enforcing sparsity. We assume that the most of candidate terms are actually irrelevant, so their coefficients should be zero. To achieve this, we use a sparse regression technique. In this work, I implemented the sequential thresholded least square method. This method works iteratively. First, we perform standard least square fit. Then, we remove coefficients that are smaller than threshold. After that, we refit the model using only the remaining terms. This process is repeated until the convergence, resulting in the sparse set of active terms that define the governing equation. One important practical challenge is the estimation of time derivatives. Since Indy requires x dot, we need to compute the derivative from data. However, numerical differentiation amplifies the noise significantly, and especially when the data is noisy. And this can be lead to the incorrect model identification or unstable results. To mitigate this issue, in this work, we used relatively clean data generated from the simulations and added controlled Gaussian noise. This allows us to systematically evaluate how noise affects the model discovery process. As a target system, I use the Duffing oscillator, which is nonlinear second-order dynamical system. This system includes a linear stiffness term nonlinear cubic stiffness term, and external periodic forcing term. The system is known to exhibit a rich nonlinear behavior, including complex phase space trajectories and sensitivity to initial conditions. Because of its nonlinear structure and forcing, it serves as a good benchmark problem for testing equation discovery method. A Dumping oscillator is widely used to model nonlinear mechanical systems, such as nonlinear structure vibrations and MEMS resonators. To generate training data, I simulate Dumping oscillator using fourth-order Runge-Kutta method. The governing equation used in this work can be written as shown on the slide, and the simulation is performed over the time horizon up to 80 seconds with fixed time step to ensure the numerical stability. The system is converted into first-order system by defining the velocity as a separate state variable. To study the effect of measurement noise, I added Gaussian noise with a standard deviation of 0.05 to both the displacement and velocity signals. In addition, I only use a portion of the trajectory, specifically the first 80 seconds for training, and the remaining data is used to evaluate the generalization of the discovered model. To compute the time derivative required by Cindy, I use the Savitsky-Golay filter, which smooths the data while estimating the derivative in more stable way compared to the naive finite differences. First, I apply Cindy to clean data without noise. As shown in the figure, the reconstructed trajectory closely matches the true trajectory in both time domain and phase space. The recovered governing equation matches the true system almost exactly, with very small error in the coefficients. The reconstruction error remains near zero, indicating that the model accurately captures the dynamics. Next, I apply the Cindy to the noisy data. As expected, noise significantly distorts the trajectory and the phase space structure. Because Cindy rely on numerical differentiation, noise introduces error in estimated derivatives, which directly affect the regression. As a result, recovered coefficient deviate from the true value, and reconstruction error increases. However, an important observation is that the overall structure of governing equation is still correctly identified. For example, the cubic nonlinearity and the forcing terms are still present. This suggests that Cindy is robust in identifying the qualitative structure of system, even in the presence of noise. To improve performance under noisy condition, I introduced denoising step using the deep ledger network, also known as LESNet. The neural network is trained to map noisy trajectory data to a smoother approximation of the underlying clean signal. By reducing high-frequency noise, the derivative estimation becomes more stable. After applying the LESNet-based denoising, the phase space structure becomes significantly clearer. When Cindy is applied to denoise data, the recovered coefficients are closer to true values, and the reconstruction error is reduced. This demonstrates that combining neural network-based denoising with Cindy can improve equation discovery performance. Here, we compare the reconstruction error across different settings. First, when we use clean data, the model achieves very low error. This is expected since the time derivatives can be accurately computed and the underlying dynamics are clearly preserved. However, this represents an idealized scenario, which is very rarely available in real-world applications. When noise is introduced, the error increases significantly. This is mainly because Cindy rely on numerical differentiation, which is highly sensitive to noise. Even small perturbation in the data can lead to large error in the estimated derivative. Therefore, incorrect identification of governing terms. To address this issue, we apply denoising step using the LesNet-based model. After denoising, the reconstruction error is reduced compared to noisy case. And this indicates that improving data quality can partially recover the performance of Cindy. However, the error is still higher than the clean data case, which suggests that denoising is not perfect and some information is still lost. Overall, this result highlights that the data quality plays critical role in equation discovery. And also, this result suggests that combining Cindy with the data-driven denoising technique can improve robustness, but there are still limitations when dealing with noise measurement. Overall, the results show that Cindy can successfully recover the governing equation of nonlinear dynamical system. And even in the presence of noise, the method is able to identify the correct structure of system. However, noise affect the accuracy of coefficients due to the instability in numerical differentiation. And by introducing some denoising step, we can improve the robustness of the method and obtain more accurate results. In conclusion, this work demonstrates that Cindy is effective tool for data-driven equation discovery. The method works well for nonlinear system and can recover governing equation directly from the trajectory data. While noise presents a challenge, combining Cindy with denoising techniques provides a promising approach for improving accuracy. And this highlights the potential of integrating machine learning with physics-based modeling.